Let me show you how to be a good Bayesian.
Folks, strap in, because today's episode is a deep dive into the fascinating world of large-scale machine learning. And who better to guide us through this journey than Sam Duffield? Currently honing his expertise at normal computing, Sam has an impressive background that bridges the theoretical and practical realms of Bayesian statistics, from quantum computation to the cutting edge of AI technology. In our discussion, Sam breaks down complex topics such as the Posteriors Python package, mini-match methods, approximate inference, and the intriguing world of thermodynamic hardware for statistics. Yeah, I didn't know what that was either. We delve into how these advanced methods like stochastic gradient MCMC and Laplace approximation are not just theoretical concepts, but pivotal in shaping enterprise AI models today. And Sam is not just about algorithms and models. He is a sports enthusiast who loves football, tennis, and squash. Oh, and he recently returned from an awe-inspiring trip to the Faroe Islands. So join us as we explore the future of AI with Bayesian methods. This is Learning Bayesian Statistics, episode 110, recorded May 31, 2024.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. What's a Bayesian? It's someone who cares about evidence.
Welcome to Learning Bayesian Statistics, a podcast about Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. For any info about the show, learnbayesstats.com is la place to be. Show notes, becoming a corporate sponsor, unlocking Bayesian merch, supporting the show on Patreon, everything is in there. That's learnbayesstats.com. If you're interested in one-on-one mentorship, online courses, or statistical consulting, feel free to reach out and book a call at topmate.io/Alex_Andorra. See you around, folks, and best Bayesian wishes to you all.
Sam Duffield, welcome to Learning Bayesian Statistics.
Thank you very much.
Yeah, thank you so much for taking the time. I invited you on the show because I saw what you guys at Normal Computing were doing, especially with the Posteriors Python package, and I am personally always learning new stuff. Right now I'm learning a lot about sports analytics, because that's always been a personal pet peeve of mine, and Bayesian statistics is extremely useful in that field. But I'm also in conjunction working a lot about LLMs and the interaction with the Bayesian framework. I've been working much more on the Baseflow package, which we've talked about with Marvin Schmidt in episode 107. So yeah, working on developing a PyMC bridge to Baseflow so that you can write your model in PyMC and then like using amortized Bayesian inference for your PyMC models. It's still like way down the road, because I need to learn about all that stuff, but that's really fascinating. I love that. And so of course when I saw what you were doing with Posteriors, I was like, oh, that sounds awesome. I want to learn more about that. So I'm going to ask you a lot of questions, a lot of things I don't know, so that's great. But first, can you tell us, give us a brief overview of your research interests and how Bayesian methods play a role in your work?
Thanks again for the invite. I think, sports analytics, Bayesian statistics, language models, I think we're going to have a lot to talk about, so it should be fun. Bayesian methods in my work. At Normal, we have a lot of problems where we think that Bayes is the right answer if you could compute it exactly. So what we're trying to do is trying to look at different approximations and different, like how they scale in different methods and different settings, and how we can get as close to exact Bayes, or the exact sort of integral and updating under uncertainty that can provide us with some of those benefits. Yeah.
Okay. Yeah, that's interesting. I of course agree. Preaching to the choir. Can you actually, do you remember when you were first introduced to Bayesian inference? Because you have an extensive background, you've studied a lot. When in those studies were you introduced to the Bayesian framework, and also how did you end up working on what you're working on nowadays?
Yeah, okay. I'll try not to rant too long about this. But so I guess mathematics at undergraduate at Imperial. So I think that we were very young at this stage. We were very young in our undergraduate, so not really sure what we want to do. At some point, it came to me that statistics within the field of mathematics is kind of like where I can that should be working on applied problems and how where the sort of field is going. And that's got me excited. Statistics at undergraduate there's different places, but you get thrown a lot of different. I mean, probably in all courses you get different point of view, and you get you get your frequentist, your hypothesis testing, and then you have your Bayesian methods as well. And it's just the Bayesian approach really sort of settled with me as being more natural. In terms of you just write down the equation, and the Bayes theorem handles. You write down, you have your forward model and your prior, and then Bayes theorem handles everything else. So you're kind of writing down. It's like mathematicians is kind of like one of the lecturers in my first year said, mathematicians are lazy. They want to do as little as possible. So Bayes theorem is kind of nice there because you just write down your likelihood, you write down your prior, and then Bayes theorem handles the rest. So you have to do the minimum possible work. You have your data, likelihood, prior, and then done. So that was really compelling to me, and that led me to my PhD, which was in the engineering department in Cambridge. So that was I had a few thoughts on what to do for my PhD. There was some more theoretical stuff, and I wanted to get into some problems, get into the weeds a bit. So engineering department at Cambridge, working on Bayesian statistics, state space models, and state space models, sequential Monte Carlo, and I think. I mean, for terminology-wise, I use state space model and hidden Markov model as the same thing. So you have this time series style data, and that was working on that sort of data gave me I feel like this propagation of uncertainty, Bayes really shines there because you need to you have to take into account your uncertainty from the previous experiments, say when you update for your new one. So that was really compelling for me, and that was I guess my route into Bayesian statistics.
Okay. Actually here I could ask you a lot of questions about those time series models. I'm always fascinated by time series models. I don't know, I love them for some reason. I find there is a kind of magic in the ability of a model to take time dependencies into account. I love using Gaussian processes for that. So I could definitely go down that rabbit hole, but I'm afraid then I won't have enough time for you to talk about posteriors. So let's not do that.
Maybe just say 1 minute. Let me say
sure.
1 minute about it. So I'll just say in terms of Gaussian process is really cool. Gaussian process can think of as a continuous time or continuous space or whatever the time varying axis. We'll call it time. Continuous time varying version of a state space model, and the state space model or hidden Markov model kind of to me is the canonical extension of just a static Bayesian inference model to the time varying setting, because and they kind of unify each other because you can write smoothing in a state space model as one big static Bayesian inference problem, and then you can write a static Bayesian inference problem, so just P of y given x, or P of recovering x from y as the first step, as a single step of state space model. So the techniques that you build just overlap, and you can at least conceptually on the mathematical level, when you actually get into the approximations and the computation, there are different things to consider, different axes of scalability consider, but conceptually I really like that. And I probably ranted for a bit more than a minute there, so apologies.
No, that's fine. I mean, I love that. And it's I have much more knowledge and experience on GPs, but I'm definitely super curious to also apply these state space models and so on. So definitely gonna read the paper you sent me about skill rating of football players, where you're using, if I understand correctly, some state space models. That's gonna be two birds with one stone. So thanks a lot for writing that.
The whole point of that paper is to say that rating systems, ELOs, TrueSkill and should be reframed as state space models, and then you just have your full Bayesian understanding of it, and you can
Yeah. I mean, for sure. I'm working myself also on a project like that on football data. And like the first thing I was doing is like, okay, I'm going to write a simple model. But then as soon as I have that down, I'm going to add a GP to that. It's like, I have to take these. I have to take these non-linearities into account. So yeah, I'm like super excited about that. So thanks a lot for giving me some weekend readings. So actually now let's go into your Posteriors package, because I have so many questions about that. So could you give us an overview of the package, what motivated its development, and also putting it in the context of large-scale AI models?
Yeah, so as I said, we at Normal think Bayes is the right answer. So we want to get we're interested in like large scale enterprise AI models. So we need to be able to scale these to big models, big parameter sizes, and big data at the same time. So this is what Posteriors Python package built on PyTorch really hopes to bring. It's built with sort of flexibility and research in mind. So really, we want to try out different methods and try out for different data sets and different goals. What's going to be the best approach for us? That's the motivation of the Posteriors package, and yeah.
Okay, and so when would people use it? Like, for instance, for which use cases would I use Posteriors?
So there's a lot of just generally fantastic Bayesian software out there, but most of it has focused on like the full batch setting, as is classically the case with the Metropolis Hastings accept reject step, and we feel like we're moving, or we've already moved into like the mini batch era, the big data era. So Posteriors is mini batch first. So if you have a lot of data, even if you have a small model and you have a lot of data, and you want to try posterior sampling with mini batches, you want to see how that if that can speed up your inference rather than doing full batch on every step, then Posteriors is the place for that, even with small models. So you can just write down your model in Pyro with PyTorch, and then use Posteriors to do that. Then that's like moving from like classical Bayesian statistics into like the mini batch one. But then there are also benefits of Bayesian, very crude approximations to the Bayesian posterior in these really large scale models. So like language models, big neural networks. These aren't going to get you. You're not going to be able to do your convergence checks and these sort of things in those models, but you might still be able to get some advantages: outer distribution detection, improved outer distribution performance, sort of continual learning, outer distribution detection. And these are the sort of things we're investigating. Is if like the sort of what if you just trained with gradient descent, you wouldn't necessarily get these things. But even very crude Bayesian approximations will hopefully provide these benefits. I think we'll talk about this more later, I think.
Yeah, okay. So basically what I understand is that you can use Posteriors for basically any model.
So, I mean, we're still young, and it doesn't have like very young, and it doesn't have like the support of I don't know, if you want to do Gaussian processes, we were not going to have a whole suite of kernels that you're going to be able to just type up. But the fundamentally, it just takes a function, a log posterior function, and then you will be able to try out different methods of that. But as I said, like the big data regime is much less researched, and the sort of big parameter regime is much harder, at least. So it's going to be it's not going to be like a silver bullet. You're going to have to. There's research. Basically, Posteriors is a tool bed for research a lot of the time, where you're going to research what inference methods you can use, where they fail, and hopefully where they succeed as well.
Okay, I see. And so, to make sure listeners understand well, you can do both in Posteriors, right? You can write your model in Posterior and then sample from it, or is that only model definition, or is that only model sampling?
So it only does approximate posterior sampling. So you write down the log posterior, you're given some data, and you write down the log posterior. So, or the joint, you could say. It doesn't have the sophisticated support of Stan or PyMC or where you actually have you can write down the model. It has the support for all the distributions and sampling and doing forward samples. It leans on other tools like Pyro or PyTorch itself for that in the normal case. It is about approximate inference in the posterior space, in the sample space. So you can do Laplace approximation, all of these things, and compare them. And importantly, it's mini batch first. So every method only expects to receive batch by batch. So you can support the large data regime.
Okay, so I think there are a bunch of terms we need to define here for listeners.
Okay. Yeah,
can you define mini batch? Can you define approximate inference, and in particular Laplace approximation?
Okay. So mini batch is the important one, of course. Yeah. So normally in traditional Bayesian statistics, if you're running random walk metropolis Hastings or HMC, you will be seeing your whole data set, all n data points at every step of the iteration. And there's beautiful theory about that. But a lot of the time in like machine learning, you have like, I don't know, 1 billion data points. Or if you're doing a foundation model, it's like all of Wikipedia is billions of data points or something like that. And there's just no way that every time you do a gradient step, or you just can't sum over 1 billion data points. So you take 10 of them, you do this unbiased approximation, and this doesn't propagate through the exponential, which you need for the metropolis Hastings step. So it rules out a lot of traditional Bayesian methods, but there's still been research on this. So this is we saw a scalable Bayesian learning is what we talk about with Posteriors. So we're investigating mini batch methods. So methods that only use a small amount of the data, as is very common in stochastic. So it's like gradient descent, stochastic gradient descent in optimization terms. So hopefully mini batch is okay. You said approximate inference. So inference is a very loaded term. Maybe I should try not to use it. But when I say approximate inference, I mean approximate Bayesian inference. So you can write down mathematically the posterior distribution, P of theta given y, and then proportional to P of theta, P of y given theta. But that you only have access to pointwise evaluations of that, and potentially even only mini batch pointwise evaluations of that. So approximate inference is forming some approximation to that posterior distribution, whether that's a Gaussian approximation or through Monte Carlo samples. So just like an ensemble of points that approximate that. So that's approximate inference, and you have different fidelities of this posterior approximation. Last one, Laplace approximation. Laplace approximation is the simplest, arguably the simplest in like the machine learning setting approximation to the posterior distribution. So it's just a Gaussian distribution. So all you need to define is a mean and covariance. You define the mean by doing an optimization procedure on your log posterior, or just log likelihood. And that will give you a point, that will give you your mean. And then you take, it gets quite in the weeds, the Laplace approximation, but ideally you then do a Taylor expansion across them. Second order Taylor expansion will give you the Hessian. We would recommend the Hessian being your approximate covariance, but there are technicalities there, and you can use the Fisher information as said. But you can read. There's lots of. I'm sure you've had people on the podcast explain it better than me.
For Laplace, no. Actually, so that's why I asked you to define it.
I'm happy to go down into the weeds of it if you want, but
Yeah, if you think that's useful, otherwise we can definitely do also an episode with someone you'd recommend to talk about Laplace approximation. Something I'd like to, I think, communicate to listeners is for them to understand. So, yeah, we say approximation, but at the same time, MCMC is an approximation itself. So
yeah,
that can be a bit confusing. Can you talk about the fact, like, about why these kind of methods, like Laplace approximation, I think VI, variational inference, would fall also into this bucket. Why are those methods called approximations in contrast to MCMC? What's the main difference here?
I would say MCMC is also an approximation in the same terminology, but yeah, the difference is that we talk about bias and asymptotically, some methods asymptotically unbiased, which MCMC is. Stochastic gradient MCMC, which is what in Posteriors, is as well under some caveats. But there are caveats for MCMC, normal MCMC as well. But yeah, so you have your Gaussian approximations from variational inference and Laplace approximation, and these are very much approximations in the sense there's no axes on which you can increase. If you increase it to infinity or if you change the posterior, you cannot do that with the Gaussian approximations unless your posterior you're known to be Gaussian, in which case is more. I mean, there might be interesting cases like that, like Gaussian processes and things. But yeah, so they don't have this asymptotically unbiased feature that MCMC does, or important sampling, sequential Monte Carlo does, which is very useful because it allows you to trade compute for accuracy, which you can't do with the Laplace approximation or VI beyond sort of like extending, like going from diagonal covariance to a full covariance or things like that. And this is very useful in the case that, yeah, you have extra compute available. So I'm a big fan of the asymptotic unbiased property because it means that you can increase your compute in safety.
Yeah, great explanation. Thanks a lot. And so yeah, so as you were saying, there is not this asymptotic unbiasedness from these approximations, but at the same time, that means they can be way faster. So it's like if you're in the right use case, in the right use case, then that really makes sense to use them. But you have to be careful about the conditions where the approximation falls down. Can you maybe dive a bit deeper into stochastic gradient descent, which is the method that Posteriors is using, and how that fits into these different methods that you just talked about?
Actually, stochastic gradient descent is not a method that Posteriors is using per se. Stochastic gradient descent is stochastic gradient descent is the workhorse of most machine learning algorithms, but Posteriors would kind of saying it shouldn't be, perhaps, or like not in all cases. Stochastic gradient descent is what you use if you have extremely large data and you just want to find the MLE, or so the maximum likelihood, or the minimum of the loss, which you might say. So that is just as an optimization routine. So you just want to find the parameters that minimize something. If you're doing variational inference, what you can do is you can tractably get the KL divergence between your specified variational distribution and the log posterior, and then you have parameters. So they're like parameters of the variational distribution over your model parameters, and then you use stochastic gradient descent like that. So this is nice because it just means that you can throw the workhorse from machine learning at a Bayesian problem and get the Bayesian approximation out. Again, as we mentioned, it doesn't have this asymptotic unbiased feature, which is maybe less of a concern in machine learning models where you have less of ability to trade compute because you've kind of filled your compute budget with your gigantic model. Although we may see this, I think this might change over the coming years, but yeah, maybe not. Maybe we'll just go even bigger and bigger and bigger. I got lost. You said you asked about stochastic gradient descent. So actually, there's something interesting to say here. And then that means
also like what the main difference characteristics of Posteriors is, like, because so that really people understand the use case of Posteriors here.
Yeah, so we didn't want to. Okay, so yeah, there's a key thing about the way we've written posteriors is that we like, where possible, to have stochastic gradient descent, so optimization, as the sort of limit under some hyperparameter specifications of the algorithms. And it turns out that in a lot of cases, so we talked about MCMC, and then we talked about stochastic gradient MCMC, which are MCMC methods that strictly handle mini-batch methods. And a lot of the time you can write down the temperature, you have the temperature parameter of your posterior distribution. And then as you take that to zero, so the temperature is like, if the temperature is very high, your posterior distribution is very heated up. So you've increased the tails, and there's like a much closer to sort of a uniform distribution. You take it very cold, it becomes very pointed and focused around optima. So we write the algorithms so that there's this convenient transition through the temperature. So you set the temperature to zero, you just get optimization. And this is a key thing about posteriors. So we have this, so the posteriors stochastic gradient MCMC methods have this temperature parameter, which if you set to zero will become a variant of stochastic gradient descent. So you can just, you sort of unifies gradient descent and stochastic gradient MCMC. And it's nice. So you have your Langevin dynamics, which tempered down to zero just becomes vanilla gradient descent. You have underdamped Langevin dynamics, or stochastic gradient HMC, stochastic gradient Hamiltonian Monte Carlo. You set the temperature to zero, and then you've just got stochastic gradient descent with momentum. So yeah, this is a nice thing about posteriors, to sort of unify these approaches, and it hopefully will make it less scary to use Bayesian approaches, because you know you always have gradient descent, and you can sanity check by just setting the temperature, just fiddling with the temperature parameter.
Okay, that's really cool. Okay. So it's a bit like the temperature parameter in the transformers that like make sure, I mean, in the LLMs, that it's like adding a bit of variation on top of the predictions that the LLM could make.
So it's exactly the same as that. So when you use it in language models for natural language generation, you temperature the generative distribution so that the logits get tempered. So if you set the temperature there to zero, you get greedy sampling. But this, we're doing this in parameter space. So it's it has
That's
this, exactly. Distribution tempering is a broad thing, particularly in, I'm going to go too philosophical, but I mean, I've first met with like tempering, and we thought about it in the settings of sequential Monte Carlo, and it's like, is it the natural way? Is it something that's natural to do? But in the context of Bayes, because Bayes' theorem is multiplicative, right? You have your P of theta, P of y given theta. It kind of makes sense to temper, because it means like, okay, I'll just introduce the likelihood a little bit, and sort of tempering is the natural way to do that, because there's multiplicative feature of Bayes' theorem. So I don't know, it kind of settled with me after thinking about it like that.
Yeah, no, I mean, that makes perfect sense. And I was really surprised to see that was used in LLMs when I first read about the algorithms. And I was pleasantly surprised, because I've worked a lot on electoral forecasting models. That's how I were introduced to Bayesian stats. And actually, I've done that without knowing it. So first, I'm using the softmax all the time, because electoral forecasting, unless you're doing that in the US, you need a multinomial likelihood. The multinomial needs a probability distribution, and how do you get that from the softmax function, which is actually a very important one in the LLM framework. And also, the thing is, your probability is not, it's like the latent observation of popularity of each party, but you never observe it, right? And so the polls, you could like conceptualize them as a tempered version of the true latent popularity. And so that was really interesting. I was like, oh damn, that's like, this stuff is much more powerful than what I thought, because I was like applying only on electoral forecasting models, which is like a very niche application you could say of these models. And no, actually there are so many applications of that in the wild.
No, it's so yeah, tempering in general is very widespread, and also I would say not particularly understood that well. Like we have this thing. There's been research in this cold posterior effect, which is quite a, I don't know, it's perhaps a annoying things for Bayesian modeling on neural networks, where you get, as I said, you have this temperature parameter that transitions between optimization and the Bayesian posterior. So 0 is optimization, 1 is the Bayesian posterior, and empirically we see better predictive performance, which is a lot of the time all we care about in machine learning, with temperatures less than 1. So like, yeah, which is annoying because we're Bayesians and we think that the Bayesian posterior is the optimal decision making under uncertainty. So this is annoying, but at least in our experiments, we found this to be this so-called cold posterior effect much more prominent under Gaussian approximations, which we only have believed to be very crude approximations to the posterior anyway. And if we do more MCMC or deep ensemble stuff, where deep ensemble is, we've got a paper will be up in our archive shortly, which describes deep ensembles. In deep ensembles, you just run gradient descent in parallel with different initializations and batch shuffling. And then you just have, you run 10 ensembles, 10 optimizations in parallel, then you've got 10 parameter things in the end. So Monte Carlo approximation posterior size 10. And then we describe in the paper that how to get this asymptotic unbiased property by using that temperature. Because as we said earlier, you have SG-MCMC becomes SGD with temperature 0, so you can reverse this for deep ensemble. So you add the noise, and then you'll get an asymptotic unbiased. Deep ensembles become an asymptotically unbiased MCMC regime, SG-MCMC. But in those cases, when you have the non-Gaussian approximation, we found much less of the cold posterior effect. So yeah, but it's still not. Maybe the cold posterior effect is a natural thing because it's not really like Bayes' theorem. Yeah, we still need to be better understood. At least in my head, I'm not sort of fully clear on whether the cold posterior effect is something we should be surprised about. But, yeah.
Okay. Me neither, if that makes you feel any better, because I just learned about that. So,
yeah, okay. I don't have any strong opinion. Huh? Yeah.
But okay, I think we're getting clearer now on the what posteriors is for listeners. So then I think one of the last question about the algorithms that's underlying all of that. So stochastic gradient MCMC. That's where I got confused. Like I hear stochastic gradient and like stochastic gradient isn't, but no, it's like SG MCMC, not SGG. So posteriors is like really to use SG MCMC. Why would you do that and not use MCMC, like the classic HMC from Stan or PyMC?
Yeah, so I mean, it's not just for SG-MCMC. There's also variational inference, Laplace approximation, extended count filter, and we're really excited to add more methods as well as we look to maintain and expand the library. Why would you use SG-MCMC? So yeah, I think we've already touched upon this. The thing is, if you've got loads of data, it's just going to be inefficient to sum over all of that data at every iteration of your MCMC algorithm, as you would, as Stan would do. So but there's mathematical reasons why you can't just do that in Stan. It's because the Metropolis-Hastings ratio has this exponential of the log posterior. But it's in log space is the only place you can get the unbiased approximation, which is what you need if you did want to naively subsample. So you can't do the Metropolis-Hastings except reject. So you have to use different toolage. And in its simplest terms, SG-MCMC just omits it and just runs a Langevin, so just runs your Hamiltonian Monte Carlo without the except reject. But there's more theory on top of this, and you need to control the discretization error and stuff like that. And I won't go into the weeds of that.
Okay,
but
thanks.
Mini batching,
yeah, okay, and that's tied to mini batching basically, like the power that SG-MCMC allows you when you're in a high data regime is tied to the mini batching, if I understand correctly.
It's the difference between MCMC and SG-MCMC. Yeah.
Okay, so that's like the main difference. Okay,
stochastic gradient. So you get you can't actually get the exact gradient like you need in Hamiltonian Monte Carlo, and for a Metropolis-Hastings step, you only get an unbiased approximation. And then there's theory about this. Is like sometimes you can deploy the central limit theorem, and then you can go covariance attached to your gradients, and you could do nice theory and improve the algorithms like that. Which
Okay. All clear now. All clear. Awesome. Yeah, and I think that's the first time we talk about that on the show. So I think it's definitely useful to be extra clear about that, and so that listeners understand, and me,
Absolutely.
like myself, so that I understand. So Thanks a lot.
It's in some setting actually much simpler because you kind of like remove the tools that you have available to you by removing that metropolis step. So it makes the implementation a bit simpler. But you kind of lose the theory in that. And then a lot of the arguments is like if you use a decreasing step size, then your noise from the mini-match, your noise from the stochastic gradients decreases epsilon squared, which is faster. So if you decrease your step size and run it for infinite time, then you'll eventually just be running the continuous time dynamics, which are exact and do have the right stationary distribution. So if you run it with decreasing step size, then you are asymptotically unbiased. But running with decreasing step size is really annoying because you then don't move as far. As we know from normal MCMC, we want to increase our step size and move and explore the posterior more. So there's lots of research to be done here, and I hope and I feel that it's not the last time you'll talk about stochastic gradient MCMC on this podcast.
Yeah, no, I mean that sounds super interesting, and I'm really interested also to really understand the difference between these algorithms, because right now that's really at the frontier of research, right? You not only have a lot of research done on how do you make HMC more efficient, but you have all these new algorithms, so like the approximate algorithms, as we said before, so VI, Laplace approximation, stuff like that. But also now you have normalizing flows. We talked about that in episode 98 with Marie-Lou Gabriel. Marie-Lou Gabriel, actually, I don't know why I said the second part with the Spanish. it's because my Spanish is really available in my brain right now, so you know.
Yeah, right,
so she's French, so that's Marie-Lou Gabriel. Episode 98, it's in the show notes. Episode 107, I already mentioned it with Marvin Schmidt about amortized Bayesian inference. Actually, do you know about amortized Bayesian inference and normalizing flows?
I know a bit about normalizing flows. Amortized Bayesian inference, I would be less comfortable with. Yeah.
Okay,
but I mean, if you could explain, I haven't watched that episode, listened to that episode, so yeah.
Yeah, I mean, we released it yesterday, so yeah.
Listening.
I'm a bit disappointed, Sam, but that's fine. Like that, it's just one day, you know. If you listen to it just after the recording, I'll forgive you. That's okay.
You bet. Yeah.
No, so kidding aside, I'm actually curious to hear you speak about the difference between normalizing flows and SG-MCMC. Can you talk a bit about that, if you're comfortable with that?
I mean, I can't. It's been a while since I've read about normalizing flows. When I did read about them, I understood it to be essentially a form of variational inference where you have a more elaborate, you define a more elaborate variational family through essentially through a triangular mapping. Like the thing why you can't just use, someone might say, why can't you use just a neural network as your variational distribution? And it's not so easy because you need to have this tractable form. Hang on a second, let me remember. But the thing is, with normalizing flows, you can get this because you can invert. That's it. They're invertible, right? Normalizing flows are invertible, so you can get this. You can write the change of distribution formula, and then you can calculate essentially just via maximum likelihood using these normalizing flows to fit to a distribution, whereas SG-MCMC doesn't. So you have to, in normalizing flows, you kind of have to define your ansatz that will fit to your distribution. I think normalizing flows are really exciting and really interesting, but yeah, you have to specify your ansatz. So it's another. So there's another tool on top, another specification on top of how you, rather than just writing the log posterior, then need to find an approximate ansatz which you think will fit the posterior or the distribution you're targeting. Whereas SG-MCMC is just log posterior, go, which is sort of what we're trying to do with posteriors. We're trying to automate, well, not necessarily automate, but trying to research approximation of that. But normalizing flows might be, as I said, I think is really interesting that you can get these more expressive variational families through like triangular mappings, invertible mappings,
Yeah, super interesting. And amortized Bayesian inference is related in the sense that you first fit a deep neural network on your model, and then once it's fit, you get posterior inference for free, basically. So I mean that's quite different from what I understand SGMCMC to be, but
yeah, for sure. Okay, yeah.
But that's also extremely interesting. That's also why I'm hammering you down on the different use cases of SGMCMC, so that myself and listeners have a kind of a tree in their head of like, oh, okay, my use case then is more appropriate for SGMCMC, or oh no, here I'd like to try multi-Bayesian inference, or I don't know, here I can just stick to plain vanilla HMC. I think that's very interesting. But thanks for that question that was completely improvised. I definitely appreciate you taking the time to rack your brain about the difference with normalizing flows.
No, I'd love to talk more on that. I'd need to refresh myself. I've written down some notes on normalizing flows, and I was quite comfortable with them. But it's just been a while since I refreshed, so I would love to refresh, and then we chat again about them, because I'd love to do a project on them, or I'd love to work on them, because I think that this invertible triangular mapping seems pretty powerful way to fit distribution to data, which is, after all, a lot of what we do.
Mm-hmm. Yeah. So that makes me think we should probably do another episode about normalizing flows. So, listeners, if there is a researcher you like who does a lot of normalizing flows and you think would be a good guest on the show, please reach out to me and I'll make that happen. Now let's get you closer to home, Sam, and talk about Posteriors again. Because, so basically, if I understood correctly, Posteriors aims to address uncertainty quantification in deep learning. Why? Am I right here? And also, if that's the case, why is this particularly important for neural networks? And how does the package help in managing, especially overconfidence in model predictions? Yeah,
so that's our primary use case at Normal, is to use Posteriors as approximate Bayes. We're getting as close to Bayes as we can, which is probably not that close, but still getting somewhere on the way to Bayesian posterior in big deep learning models. But we built Posteriors to be as modular and general as possible. So as I said, if you have a classical Bayesian model, you can write it down in Pyro, but you've got loads of data, then okay, go ahead. And Posteriors should be well suited to that. In terms of what advantages we want to see from uncertainty quantification, or this approximate Bayesian inference in deep learning models, there are three sorts of key things that we distilled it down to. You mentioned confidence in outer distribution predictions. So we should be able to improve our performance in predicting on inputs that we haven't seen in the training set. I'll talk about that after this. The second one is continual learning, where we think that if you can do Bayes' theorem exactly, you have your prior, you get some likelihood, and you have your likelihood, you get some data, you have a posterior, then you get some more data. And then your posterior becomes your prior, and you do the update. And you can iterate like that if you can do Bayes' theorem exactly. And then, you can extend it even further, and then you have, with some sort of evolution along your parameters, and then you have a state space model, and then the exact setting, linear Gauss, and you've got a count filter. So continual learning is in this case, Bayes' theorem does that exactly, and in continual learning research in machine learning setting, they have this term of avoiding catastrophic forgetting. So if you just continue to do gradient descent, there was no memory there. So you would just, apart from the initialization, so you would just forget what you've done previously, and there's lots of evidence for this, whereas Bayes' theorem is completely exchangeable of the order of the data that you see. So you're doing Bayes' theorem exactly, there's no forgetting. You just have the capacity of the model. So that's where we see Bayes sort of solving continual learning. But as I said, you can't do Bayes' theorem exactly in a billion-dimensional model. And then the last one is we'll call it like decomposition of uncertainty in your predictions. So if you just have gradient descent model and you're predicting reviews, someone's reviews, and you have to predict the stars, it will just give you, as you said, it gives you your softmax. It will just give you this distribution over the reviews, and it'll be like that. But what you really want is you want to have some indication of like outer distribution detection, right? You want to know, okay, I'm confident in my prediction. And you might get a review that is like, the food was terrible, but the service was amazing, or something like that. Like views were amazing, food was terrible. And then, like, let's say we're perfect models, say, of this. We know how people review things, but we couldn't give, we'd have quite a lot of uncertainty under that review because we don't know how the reviewer values those different things. So we might have just a completely uniform distribution over the stars for that review. But we'd be confident in that distribution. But what Bayes gives you is it gives you the ability to, this sort of this second order uncertainty quantification, is if you have this distribution over parameters and you have a distribution over logits at the end with predictions, you can identify, you can split between, from information theory, it's called aleatoric and epistemic uncertainty. Aleatoric uncertainty or data uncertainty is what I just described there, which is just natural uncertainty in the model and the data generating process. Epistemic uncertainty is uncertainty that was removed in the infinite data limit. So that would be where the model doesn't know. So this is really important for us to quantify that. Okay. I ranted a bit there. I can, in like 30 seconds, elaborate on the point you specifically mentioned on outer distribution performance and improving performance in outer distribution. And I think that's quite compelling from a Bayesian point of view, because what Bayes says on like a supervised learning setting is said, gradient descent just fits one parameter, finds one parameter set configuration that's plausible given the training data. Bayes' theorem says, I find a whole distribution of parameter configurations that's plausible given the data. And then when we make predictions, we average over those. So it's perfectly natural to think that a single configuration might overfit and might just give, it might just be very confident in its prediction when it sees outer distribution data. But it doesn't necessarily solve a bad model, but it should be more honest to the model and the data generating process you've specified, is if you average over plausible model configurations under the training data when you have your testing. So that's sort of quite a compelling, to me, argument for improving performance on outer distribution predictions, like the accuracy of them. And there's a fair bit of empirical evidence for this, with the caveat again being that the Bayesian posterior in high dimensional models, machine learning models, is pretty hard to approximate. Cold posterior effect, caveats, these things.
Okay, yeah, I see. Yeah, super interesting. So now I understand better what you have on the Posteriors website about the different kind of uncertainties. So definitely that's something I recommend listeners to give a read to. I've put that in the show notes. So both your blog post introducing Posteriors and the docs for Posteriors, because I think it makes that clear. It makes that clear combined to your explanation right now. And something I was also wondering is that, if I understood correctly, the package is built on top of PyTorch, right?
Yeah, that's correct. Yeah.
Okay. So, and also, did I understand correctly that you can integrate Posteriors with pre-trained LLMs like Llama 2 and Mistral, and you do that with a Hugging Face Transformers package?
So Posteriors open source. We're fully supported the open source community for machine learning, for statistics, which is and in terms of we're sort of in the fine-tuning era, or there's so much. There are these open source models, and you can't get away from them. We have that Llama 2, Llama 3, Mistral, and basically we want to harness this power, right? But we, as I mentioned previously, there are certain issues that we like to remedy with Bayesian techniques. So the majority of these open source models are built in PyTorch. I'm also a big JAX fan. I also use JAX a lot. So I was very happy to see and work with the torch.func sublibrary, which basically makes it you can write your PyTorch code and you can use Llama 3 or Mistral with PyTorch, but writing functional code. And so that's what we've done with Posteriors. And yes, you can, so yeah, Hugging Face transformers you can download the models, that's where all they're hosted, and how you access them. But then what you get is just a PyTorch model. It's just a PyTorch model. So it's just and then you throw that in and it composes them all nicely with the Posteriors updates, or you write your own new updates in the Posteriors framework, and you can use that as well. Still with Llama 3 or Mistral, and
okay,
fine-tune
nice.
your own data.
And so what does it mean concretely for users? That means you can use these pre-trained LLMs with Posteriors, and that means adding a layer of uncertainty quantification on top of those models?
Yeah, so you need, I mean, Bayes' theorem is a training theorem, so you need data as well. So you take your pre-trained model, which is transformer, or it could be another type of model, it could be an image model or something like that, and then you give it some new data, which we would say was fine tuning, and then you use Posteriors to combine the two, and then you have your new model out at the end of the day, which has uncertainty quantification. It's difficult, as I said. We're sort of in this fine tuning era as open source large language models. It's still this is different. There's still lots of research to do here, and it's different to our classical Bayesian regime where we just have there's only one source of data and it's what we give it. In this case, there's two sources of data because you have your data, whatever Llama 3 saw in its original training data, and then it has your own data. It's, can we hope to get uncertainty quantification and the data that they used in the original training? Probably not, but we might be able to get uncertainty quantification and improved predictions based on the data that we've given it. So there's lots for us to try out here and learn, because we are still learning on this in terms of the fine tuning setting. But yeah, this is what Posteriors is there to make these sorts of questions as easy as possible to ask and answer.
Okay, fantastic. Yeah, that's so exciting. It's just like, and it's a bit frustrating to me because I'm like, oh, I'd love to try that and learn on that and like contribute to that kind of packages. At the same time, I have to work. I have to do the podcast, and I have other packages I'm already contributing to. So I'm like, oh my god, too much choices, too many choices.
No, come on, Alex. I'm gonna see. We're gonna see again, Alex. Pull request. It's soon enough.
Actually, how does this ability to have the transformers and use these pre-trained models, does that help facilitate the adoption of new algorithms in Posteriors? Because if I understood correctly, you can support new algorithms pretty easily, and you can support arbitrary likelihoods. How do you do that?
I wouldn't say that the existence of the pre-trained models necessarily allows us to support new algorithms. I feel like we've built the Posteriors to be suitably general and suitably modular, that it's kind of agnostic to your model choice and your log posterior choice. In terms of arbitrary likelihoods, but yeah, that's like a benefit though. That's like the arbitrary likelihoods is relevant because a lot of machine learning packages, or a lot of machine learning is essentially just boils down to classification or regression, and that is true. And because of that, a lot of machine learning algorithms a lot of machine learning packages will essentially constrain it to classification or regression. At the end, you either have your softmax or you have your mean squared error. Yeah, softmax cross entropy or mean squared error. In Posteriors, we haven't done that. We're more faithful to the sort of the Bayesian setting where you just write down your log posterior and you can write down whatever you want. And this allows you greater flexibility in the case you did want to try out a different likelihood, or like even in like simple cases, like it's just more sophisticated than just classification or regression a lot of the time. Like in sequence generation, where you have this sequence and then you have the cross entropy over all of that. It just allows you to be more flexible and write the code how you want. And there's additional things to be taken into account. Like sometimes if you were doing a regression, you might have knowledge of the noise variance, and that's just the observation noise variance, and that's just much easier to if we don't constrain like this, it's just much easier to write your code, much cleaner code than if you were. And it's also future proofing. We don't know what's going to be happening in going forward. We may see multimodal models. We may see like text and images together. In which case, we will support that. You have to supply the compute and the data, which might be the harder thing, but we'll support those likelihoods.
Okay, I see. Yeah, that's very, very interesting. And is that related to the fact that I think I've read in your blog post or on the website that you say that posteriors is swappable. What does that mean? And how does that flexibility benefit users?
Yeah, so I mean, this is the point of swappable is that when I say that is that you can change between if you want to if you think. As I said, Posteriors is a research toolbox, and it's to us to investigate which inference method is appropriate in the different settings, which might be different if you care about decomposing predictive uncertainty, and it might be different if you care about avoiding catastrophic forgetting and continual learning. So the thing is that you can the way it's written is you can just swap. You can go from SGHMC and you can go to Laplace approximation, or you can go to VI just by changing one line of code. And the way it works is you have your builds, you have your transform equals posteriors dot inference method dot build, and then any configuration arguments, step size, and things like this, which are algorithm specific. And then after that, it's all unified. So you just have your init around the parameters that you want to do Bayes on, and then you iterate through your data loader, you iterate through your data. And then it just updates based on the batch, and batch can be very general. So that's what it means. So you can just change one line of code to swap between variational inference and SGHMC or extended Kalman filter or and all the new methods that the listeners are going to add in the future.
Okay, I see. And so I have so many more questions for you on Posteriors, but let's start and wrap that up, because I also want to ask you about another project you're working on. So maybe to close that up on Posteriors, what are the future plans for Posteriors, and are there any upcoming features or integrations that you can share with us?
So we're quite happy with the framework at the moment. There's lots of little tweaks that we have a list of GitHub issues that we want to go through, which are mostly and excitingly about adding new methods and new applications. So that's really what we're excited about now, is to actually use it in the wild and hopefully experiment all these questions that that we've discussed. Like how does it make sense, and how we get the benefits of Bayesian true Bayesian inference on fine tuning or on large models or large data. And so we're really excited and to add more methods. So if listeners have mini batch big data Bayesian methods that we want to try out with a large data model, then we're hopefully accepting that. We will. I do promote generality and doing it in a way that is sort of flexible and stuff. So we may think a lot. It's not. We want to add methods that somehow feel natural and ways to extend and compose with other methods. So it might be that if we've got some very complicated last layer requires just for classification method, we're probably not going to add it. So it has to be methods that stick within the Posteriors framework, which is this arbitrary likelihood Bayesian swappable computation.
Okay, yeah, that makes sense. Because you have you have that kind of vision of wanting to do that and having that as a research tool, basically. So yeah, that makes sense to keep that under control, let's say. Something I want to ask you in the last few minutes of the show is about thermodynamic compute. I've seen you are working on that, and you've told me you're working on that. So yeah, I don't know anything about that. So can you what's that about?
Yeah, so I mean, this is something that's very normal computing, and is it's something that we have. Yeah, we have this hardware team. It's like a full stack AI company, and on the posterior side, on the client side, we look at how we can bring in principal Bayesian uncertainty quantification and help it solve the issues with machine learning pipelines, like we've already discussed. And on the other side, there's lots of parts to this. More just like traditional MCMC is difficult sometimes because, it's just like about simulating SDEs. Essentially, is what the thermodynamic hardware is. Simulating SDEs. Normally, you have this real pain with the step size, and as the dimension grows, step sizes get really small. And so, SDEs. Where do we see SDEs? You see SDEs in physics all the time, and physics is real. We can use physics, so it's building physical hardware, analog hardware that we can hopefully that evolves as SDEs, and then we can harness that SDEs by encoding, like currents and voltages and things like that. So I'm not a physicist, so I don't know exactly how it is, but I'm always reassured at how when I speak to the hardware team, how simple they talk about these things. It's like, yeah, we can just stick some resistors and capacitors on a chip, and then it'll do this SDE. So this is and then we want to use those SDEs for scientific computation. And with a real focus on statistics and machine learning. So yeah, we want to be able to do HMC on device, on analog device. The first step is to do with a linear, so with a Gaussian posterior or with a linear drift in terms of this. This is an Ornstein-Uhlenbeck process, and we've developed hardware to do this. And turns out that an Ornstein-Uhlenbeck process, because it has a Gaussian stationary distribution, and you have this, you can input the precision matrix and output the covariance matrix. That's matrix inversion. So, and your physical device just does this, and it's because it's an SDE, it has noise and is kind of noise aware, which is different to classical analog computation, which is historically been plagued, which is really old, but historically been plagued by noise. And it's like, yeah, there's all this noise in physics, and because we're doing SDEs, yeah, we want the noise. So yeah, that's the whole idea. It's obviously very young, but it's fun. It's fun stuff. Yeah.
So that's basically to accelerate computing. That's hardware first, so that computing is accelerated.
We want to. I mean, it's a baby field, so we're trying to accelerate different components. What we worked out is with the simplest thermodynamic chip we can build is this linear chip with an Ornstein-Uhlenbeck process, and that can speed up with some error, but it has asymptotic speedups for linear algebra routines, so inverting a matrix or solving a linear system, and that's awesome. So in this case, it would speed up a certain component, but that could be useful in like a Laplace approximation or these sort of things, also in machine learning.
Okay, yeah, that must be very fun to work on.
Yeah.
Do you have any writing about that we can put in the show notes? Because I think it'd be super interesting for listeners.
Yeah. We've got the normal Computing Scholar page has a list of papers, but we also have more accessible blogs, which I'll make sure to put in the show notes. Sure.
Yeah, please do, because I think it's super interesting, and when you have something to present on that, feel free to reach out, and I think that'd be fun to do an episode about that. Honestly, that'd be great.
Oh, thank you.
Yeah. So maybe one last question before asking you the last two questions. Let's dezoom, be way less technical. We've been very technical through the whole episode, which I love.
Okay.
But maybe I'm thinking, if you have any advice to give to aspiring developers interested in contributing to open source projects like Posteriors, what would it be?
Okay, yeah, I don't know. I don't feel like I'm the best, necessarily the best place to say all this, but yeah, I mean, the most important thing is just to go for it. Just get stuck in, get in the weeds of these libraries and see what's there. And there's loads of people building such cool stuff, and it's all in the open source ecosystem, and it's really fun it's really fun and rewarding to get involved for it. So just go for it. You'll learn so much along the way. Something more tangible, I find that when I'm stuck on I don't understand something in code or mathematics, then I often struggle to find it in papers per se, and I find it textbooks. I love textbooks. Textbooks I find as a real source of gold for these, because they actually go to the depths of explaining things without having this sort of horse in the race style writing that you often find in papers. So yeah, get stuck in, check textbooks if you get lost or I don't understand, or just ask as well. Open source is all about asking and communicating and bouncing ideas. So
yeah, for sure. Yeah, that's usually what I do. I ask a lot, and I usually end up surrounding myself with people way smarter than me. And so
that's exactly what you want. That's what you want.
It's exactly how I learned. Yeah, because textbook I see, I would say I kind of find the writing boring most of the time. Depends on the textbooks, and also it's expensive. So yeah. So that's kind of the problem of textbooks, I would say. I mean, you often can have them in PDFs, but I just hate reading a PDF on my computer. So I want the book object, or having it on Kindle or something like that, but that doesn't really exist yet. So could be something that some editors solve someday. That'd be cool. I'd love that. Awesome, Sam. That was great. Thank you so much. We've covered so many topics, and I have my brain is burning, so that's a very good sign. I've learned a lot, and I'm sure our listeners did too. Of course, before letting you go, I'm going to ask you the last two questions I ask every guest at the end of the show. So, one, if you had unlimited time and resources, which problem would you try to solve?
I mean, this is such a question. Yeah, it's a great question, but such a hard one to ask there as well. I think that. I mean, this is what I'm saying. Sam now, May 2024, says that. I mean, one thing I'm really passionate about, and I think that gets lost a lot in machine learning, or as in sports analytics too, in ELO, is that we really want to decouple the model specification, the data generating process, how you go from something you don't know to the data you do have. That's your freedom as a data modeler. How do you define that? From the inference and the mathematical computation. So that's the way you do your approximate Bayesian inference. And you want to decouple those. You want to make it as easy as possible. Ideally, we just want to be doing that one. We just want to be doing the model specification. And this is Stan and PyMC do this really well. It's just you write down your model, we'll handle the rest. And that's kind of the dream we have as Bayesians or Bayesian software developers. And it's so with Posteriors, we're trying to do something like this moving towards this for bigger machine learning models, and so bigger models, bigger data settings. So that's kind of the dream there. But then in machine learning, what does machine learning have differently to statistics in that setting? It's machine learning models are less interesting than classical Bayesian models. They're less. The thing is, they're more transferable, right? It's just a neural network, which we believe is machine learning and will solve a whole suite of tasks. So perhaps in terms of the machine learning setting, where we decouple modeling and inference and data, you kind of want to remove the model one as well. You want to have these general purpose foundational models, you could say. So really, you want to let the user focus. And so we're handling the inference. We're also handling the model, so really let the user just give it the data and say, okay, let's do this data and let's use this data to predict other things, and let the user handle that. So that's potentially a real unlimited time and resources. Plenty of resources need to do that, but that's Sam May 2024's answer.
That sounds amazing. I agree with that. That's a fantastic goal. Also that reminds me, that's also why I really love what you guys are doing with Posteriors, because it's trying to, now that we start being able to get there, making Bayesian inference really scalable to really big data and big models. I'm super enthusiastic about that. It would be just fantastic. So thank you so much for taking the time to do that, guys.
Yeah, we're doing it. We're going to get there.
Yeah. Well, I love that. And second question: if you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be?
I was a bit intimidated this question. Yeah, you ask everyone, and again, it's a great question. But then I thought about it for a little bit, and it wasn't too hard for me. I think that David Mackay is someone who, has done amazing work. David Mackay is doing Bayesian neural networks in 1992, and that's like crazy before I'm born. Anyway, Bayesian neural networks in 1992. Then I've just been going through his textbook. As I said, I love textbooks. So going through his textbooks on information theory and Bayesian statistics. He is a Bayesian, or was a Bayesian. Information theory and statistics. And there's something that he says, like right at the start of the textbook, is like, one of the themes of this book is that data compression and data modeling are one and the same. And that's just really beautiful. And we talked about stream codes, which in a very information theory style setting, but it's just an autoregressive prediction model, just like our language model. So it's just someone who has the ability just to distill these informations and do these distill information and help with unification and be so ahead of their time. And then additionally, with a sort of like groundbreaking book on sustainable energy, so like also tackling one of the greatest challenges we have at the moment. So that's the sustainable energy book is really wonderful and one of my favorite books I've read.
Nice, yeah. Definitely put that in the show notes, I think.
Yes, definitely, yeah.
Yeah, I'd like to give that a read. So, yeah, please also put that in the show notes. That's going to be fantastic. Great. Well, I think we can call it a show. That was fantastic. Thank you so much, Sam. That, like, really, I learned so much, and now I feel like I have to go and read and learn about so many things. And I can definitely tell that you're extremely passionate about what you're doing. So, yeah, thank you so much for taking the time and being on this show.
No, thank you very much. I had a lot of fun. Yeah, thank you for being partial to my rantings. I need that sometimes.
Yeah, that's what the show is about. Like my girlfriend is extremely happy that I have this show to rant about Bayesian stats and any nerdy stuff.
Yeah, so true. Yeah.
Well, Sam, you're welcome. Anytime you need to do some nerdy rant.
Oh, thank you. I'm sure I'll be back.
This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and follow the show on your favorite podcatcher, and visit learnbaystats.com for more resources about today's topics, as well as access to more episodes to help you reach true Bayesian state of mind. That's learnbaystats.com. Our theme music is Good Bayesian by Baba Brinkman, feat. MC Lars and Mega Ran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbaystats. Thank you so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.